It's a real pleasure today to be telling you about our work engineering swarms across scales, from nanoparticles for cancer treatment to larger robots that could be useful for logistics. And hopefully some of these swarms will be deployed in the real world. What fascinates me is this flock of birds and the ability of these birds to work together. And there's many features that are useful for real-world engineering. For example, if you add birds to the flock, it continues to fly, so it can scale to huge numbers. If a bird falls to the ground, the whole flock doesn't crash, so they're robust to individual failure. And together they can do more than the sum of their parts. And these beautiful dances in the sky are not the result of one leader bird telling every bird what to do, but it's the result of every bird reacting to their local environment. And once you see examples of swarming in nature, you start to see it everywhere, whether it's ants creating trails to your picnic table, or bees and their ability to make decisions about their next nest site, and indeed our ability to grow fully functioning human beings from just a couple cells. So as a swarm engineer, we have a puzzle. We have collective behaviors, swarm behaviors we like to design, and what we need to do is figure out how to design the individual agents and their local interactions. And we take two approaches to doing that. One is to do bioinspiration. So people have been studying the birds and the ants and the bees and cells and can give us rules that we can then implement in artificial systems. But sometimes that's not possible if there's a specific swarm behavior you'd like to achieve for an application, for example, in which case you need to explore the design of the agent and its local rules. And you could explore by guessing behind your laptop. You could explore by having lots of people helping you guess, which is a form of crowdsourcing. Or what we increasingly do is use machine learning. In our case, we use artificial evolution to automatically come up with the rules that give you the desired swarm behavior. So taking bioinspiration, what's exciting is once you have the rules of flocking, for example, you can put them on a swarm of flying robots. Here, this is work we did at the Floriano lab. And you can predict what should arise. We knew that the dances in the sky should form circles. Here you can see their GPS trajectory. And if you've designed your system, it should emerge in the way that you'd predicted. And that was really a really fun project to work with. It was very exciting. But in my mind, swarms in nature worked in much larger numbers. And so I got excited about the idea of nanomedicine. And I spent 3 years in a laboratory at MIT with Sangeeta Bhatia. And what's exciting about nanoparticles is because of their size, they're quite good at leaking out of certain vessels into certain types of solid tumors. And so that makes them interesting vehicles for the delivery of drugs to these tumor environments. And these nanoparticles work in the 10 to the power 13. So that was a big number that I thought we could have some fun with. And in her laboratory, they made particles of different sizes, particles of different shapes, particles with different charges. Some of these particles were made out of materials that were energy receptive, so you could use light or magnetic fields to activate them. And you could decorate these nanoparticles with molecules that allowed them to stick, for example, to receptors on the surface of some cancer cells. You could also load them with a payload that you could release in a more or less controlled fashion. So with the flying robots you saw before, I designed a program, and that's what made the flying robots swarm. In the case of the nanoparticles, we have all these knobs that we can turn on the design of the nanoparticle, its size, its shape, its charge, its coding, its cargo. And so that's how we modify the behavior of the collective. And this is just an example of turning two knobs, how sticky a particle is and how big it is, which changes how fast it moves. And this is a very simple example, but just those two knobs give you completely different distributions within a tumor tissue. Bioengineers, for example, thought it would be a good idea to make these particles very sticky. So they would stick to the cancer cells and then kill the cancer cells. And if you test this in a dish, everything is well mixed. You put this sticky particle, it kills all the cancer cells. It sounds like a great idea. But if you do this, thinking of the dynamics of the system, what happens is the sticky particle leaks out of the vessel. They all stick to the same cancer cells, and they never go deep in this tumor tissue to kill the remaining cancer cells. So that's a good example where understanding how the design of the body of these particles impacts their collective behavior matters. And this is something that we study increasingly with sophisticated simulations that allow us to predict where these nanoparticles will go. And here in the bottom is a microfluidic device, a little tumor on a chip. in my lab so that we can visualize where these nanoparticles go as well. And the bigger picture is, can we actually automate the design of nanoparticles for specific patients? So ideally what we would have is a patient or a certain type of tumor with its specifications. We would then grow a virtual tumor. And then using this virtual tumor, we would cut out lots of little tumor slices. And we would use, in our case, artificial evolution to turn those knobs on the design of the nanoparticle so that you optimize this nanoparticle to kill all these little slices of tumor tissue for this specific tumor scenario. So we also wanted to use this platform to understand how we could create more swarmy behaviors. And so we created a game called NanoDoc to crowdsource the design of these particles. And in this game, there were cancer cells, there were healthy cells, because of course the solution, if there's no healthy cells, is to dump loads of drug, but that would not be specific. It would kill the healthy cells, so we need to be more specific. You can change the dosage of the nanoparticles. You can combine particles. You can change its size, which changes its motion. Some of these cancer cells have receptors on their surface, and some of the particles can stick to those receptors with different strengths. You can load the particle, and you can make a smart material where if something binds to the particle, it releases something in its environment, and you can self-assemble and disassemble the particle. So looking at it from a swarm roboticist perspective, these particles can sense their environment, they can act on their environment by releasing something. That thing they release can trigger another nanoparticle, so now you have communication. And while they can't go left or right like the flying robots I showed you, they can speed up and slow down through self-assembly and disassembly. So this game was played over 120,000 times. Here's an example of a sticky particle design, and you can just tweak the binding strength of this particle to show that it distributes better over the tumor tissue. But they also came up with all sorts of creative ways of designing nanoparticles. And we also used this game to explore some of the swarmy behaviors we knew from robotics. So here what you're seeing in simulation is a trail formation algorithm. You can see this trail go from the upper left corner to the bottom right corner. Now, there's not just nanoparticles that work in huge numbers and tiny sizes. There's bacteria, mammalian cells, protocells, and all of these have important applications in the biomedical field. And the challenge that we have is for all these systems, if we wanted to actually implement the right body, because that's how we program them, we would need a chemist or a bioengineer spending a lot of time figuring out how to tune the dynamics of these systems. And so we wanted to design a new playground for these micro and nano swarms. And that's why we built the dome for dynamic optical microenvironment. The dome is all open hardware. You can print it yourself with all off-the-shelf components. It costs 700 pounds to make. And what it is a projector with thousands of pixels. Each one of these pixels can act on the size of a cell, and that projects on our micro swarm. And then we have a camera to observe what's happening in our sample so that we can change what gets projected in the system. And so at first we wondered, can we build the building blocks of swarming and use this to augment our agents? So here what you're looking at is living volvox, which are little algae. And in this first video, we're giving them communication capabilities. So we're giving them communication by projecting light halos on them in blue. And then these light halos propagate through the swarm. Here what you're looking at in the middle video is these living volvox, so the real agents depositing light in the environment. So that's a form of stigmergy, modifying the environment. Turns out they react to light. So you see this little volvox stops in its tracks when it reaches the light. And this third building block for swarm behaviors, which we think will be useful in the future, is a form of motion control. So here zapping the volvox stops them in their track as well. And we use Q-learning to optimize the zapping for individual volvox, because every volvox is slightly different. You can also modify this system because we've built it from the ground up. So we're working with biologists to understand if we can make a wearable dome to do things like wound healing. And here what you're looking at is a video from our dome with cells with a wound in them and the wound closing. And we're understanding if we can use light at that frontier to help guide the wound healing process. And we're creating more fantastic little creatures. So on the left, you see an artificial evolution approach where we have tiny little bubbles and they can contract and they can expand using light. And so we evolved them to figure out what topologies would give us best locomotion. And on the right, you see some new materials we're playing with chemists that have this capability of retracting and expanding using light. So that was a deep dive in the nano and the micro world and what we can think of in terms of bioinspiration. But that really changes the way we think of robots at a larger scale. So if you're thinking of robots for farming, planting seeds, you might imagine a tractor robot that zigzags through that field and plants seeds sequentially. But if you think in the same way as we think at the nano and the micro scale, maybe you'd be making 100 million robot seeds that are just little bubbles with just the right amount of nutrients that diffuse over the farm field and plant themselves. And what does this build on? Well, just like the micro and the nano world, it builds on random motion, very simple local interactions. So here you're seeing a swarm of kilobots that we have in the lab based on Radhika Nagpal and Mike Rubinstein's design. And here, random motion, very simple local interactions, they can create the trail you saw in the nanoparticle simulator. Here, random motion, very simple local interactions, a swarm of 400 of these kilobots in the lab are deciding between blue and red. Let's just reset that. And they converge to blue based on an algorithm inspired from honeybees. And here what you're looking is morphogenesis, so the ability to grow shapes by having robots that behave as cells, exchanging simple chemical information and reacting this chemical information and transmitting it to their neighbors. And this gives rise to spots and patterns, and those spots allow for the growth of limb-like structures. You can see these protrusions come out. And because it's all self-organized, you can chop off the limbs and they regrow, you can split the swarm, and it self-heals. So we get a lot of features for free by thinking about huge numbers of very simple agents, because this number allows us to be very adaptable. And you can imagine that if we were to make this many robots, we would need to rethink how we design robots to perhaps not make them out of metal or materials that are not so sustainable. And so we're also wondering what a robot might look like that could be mass produced. Maybe a little tree that could pop out robots. They would be preloaded. For example, here we're preloading them by folding them. You can paint them with sensors if that's what you like to do, or maybe you decorate them with seeds. And we use water to trigger the release mechanism. So if it rains, that would allow these robots to jump around their environment. Now, the robot that you're seeing here is a robot currently made out of plastic. But this is a picture from the lab where we're actually testing lots of material like wood to see if some of these materials could biodegrade and still have these jumping properties that are quite useful. So that was a lot of bioinspiration. I mentioned exploration as well. So on the exploration front, what we're lucky in robotics is that we have increasingly sophisticated hardware platforms and more computation that we can use on board them. So this is a new swarm that was designed by Simon Jones. And what he did is he took the epochs, if you know those robots, and he put GPUs on board each one of them. And what that allows the robots to do is run an evolutionary algorithm on board each robot, and the swarm collectively learns how to push this frisbee from one side of the arena to the right side of the arena. And it takes 15 minutes in real time to go from not knowing how to do this task to getting better and better at it. It doesn't require any external computation. It allows for helping closing the reality gap because you're able to test things as you go along in reality, and you can recalibrate your simulations if that's useful. Now, we've done evolution in the past. In my case, I did it a lot using neural networks, and the challenge with that is they tended to be black boxes. And so if you wanted to deploy these in the real world, it made it a little challenging. And so what we've been focusing on is the development of behavior trees, and that's what we evolve with our systems, so that when the evolutionary process is finished, like you saw in that video before, you're left with a tree that you can parse, that you can reason about, that you can understand. You can build tools around it, like the simulator on the right, where we color code the behaviors, and we can try to understand what emerged from that evolutionary process and build confidence in the solution. So I think we're at a stage where we can build large numbers of simple robots, smaller numbers of more sophisticated robots. We can design algorithms using bioinspiration or automatic design. And it's time now to think about how we make these useful for people. So how do we do that? Well, we ask people. And we spent time making an escape room. This was when we were still allowed to lock people into closed spaces. And this escape room helped people learn about swarm robotics. It took them about 40 minutes to learn about the technology and break out of this escape room. And then we asked them what they would use it for. So there are some things we knew about, like farming, search and rescue, cleaning the ocean, that type of application. construction, but also some that we hadn't thought of, like massages, who knows? And then we digged in a little bit deeper and did use case studies with potential users. We spoke with logistics users, with firefighters. This is in front of our laboratory in Bristol, them coming for a use case study, and those who do inspection of bridges. And what was exciting is they saw the potential of swarm robotics. We didn't have a science fiction discussion as long as it was designed with them in mind, and as long as it was designed in a way to make it trustworthy. And in particular, what got me excited was this unmet need in logistics. So when you think of logistics robots, you might think of Amazon robots. So a very structured environment designed to a certain extent for the robots, loads of R&D that goes into that. And that's not something that can be deployed in a small retail shop or a pop-up warehouse. And so there's a huge unmet need when we spoke to users of them wanting robots, but not being able to adopt them because they wouldn't work in their real world, messy environments. And that, I think, is where swarms, might be able to shine. I think they have the potential to be used as an out-of-the-box swarm solution because they rely on local information rather than this grand planning that is often necessary with other types of solutions. But it also takes thinking differently about the problem. So if you think of logistics, usually people will, put forward the key performance indicators. It has to do with cost and speed very often. But what about the swarm performance indicators that make these useful out of the box for this unmet need? What about robustness, scalability, adaptability, the fact that you might not need any infrastructure and ideally no setup time if we manage to make these usable out of the box? So what might this look like? I just want to do a little thought experiment with you. Let's say that at IROS there was a robotic cloakroom and you're the operator of the cloakroom. Well, you could have designed this in a centralized way. How would you have done this? You would have arrived, mapped the cloakroom environment. There would be a central computer. People would arrive with their jackets to the central computer, and the central computer would say, robot 321, follow this trajectory and pick up this jacket. The user puts their jacket in there, and then the central computer says, robot 321, follow this trajectory, put this jacket here, store it in the database, and when the user comes back, they're able to request their jacket, it gets looked up in the database, and that robot then brings back their jacket. So that's a situation where you need good comms, you need a map of the environment, you need an up-to-date database to know exactly where everything is. How would this work using a swarm solution? Well, maybe you would arrive as the operator and put tape on the floor and say, this is the swarm cloakroom. You would then have users who arrive with a Bluetooth app anywhere around that environment and say, I have a jacket for you. A nearby robot would sense that signal and come to the user. You'd put your jacket in that box, and then the swarm robot would put it anywhere in the cloakroom environment. It doesn't really matter. And when the user comes back, they would take their Bluetooth app, they would say, hey, has anyone seen my jacket? And then every robot looks around, which is what we do in human cloakrooms, by the way. And then they would find that box, that box with the jacket and bring it back to that user nearby. And by the way, if the user finds it quicker, they could walk through, pick up their jacket from the box and leave that cloakroom environment. So that's a case where there is no map. There's not a need for central communication. You don't even need a database. And really the power comes from the ability of these robots to understand and react to their local environment. But we need new kinds of robots to think about this distributed situational awareness. And so we've built in collaboration with Toshiba these new robots called DOTS for Distributed Organization and Transport Systems. So what are DOTS? DOTS are pretty sophisticated robots for the swarm world. They've got a GPU and 6 CPUs. They have 4 cameras. They have a laser time of flight, range sensor. They have a lifting platform so that we can lift things. They're driven by drone motors, so they're very fast. They have omnidirectional movement. And they have 6 hours of battery life. And using this onboard power, we're able to build a new swarm that can understand its local environment and use this understanding to do interlogistics tasks or other industrial applications that we might explore in the future or construction. And so here what you're looking at is a swarm. They're doing random motion, but you could implement another algorithm. That's not the most important aspect. It's that they understand that local world around them. And they are able quite rapidly to deploy these algorithms that we ask them to deploy and test things in these more realistic settings. So beyond the interlogistics, we're also exploring other real world scenarios. One is the deployment of large swarms of drones to cover areas the size of California for the monitoring and mitigation of forest fires. Here you're seeing an example on the smaller drones, just as a demonstration. But the key question we have here is not just the algorithms to cover these huge areas, but how would a swarm operator be able to optimize the algorithms, monitor the algorithms, and control the algorithms all in real time. And so this is part of a big project on how we design swarm operation, also considering the human factors. And this is our latest social swarm. So here what you see is a swarm of 100 tiles. They're part of a swarm called mosaics. And these tiles here, we can use them in social settings. What they're doing here is in a mall in Bristol, they're asking passerbys about climate change, and then they serve as physical avatars of people's opinions. So this is to help people who might not share their opinion, to engage people who might not otherwise engage with this concept. And it's also just a great way to have both robot swarms and human swarms working together towards big questions. And we've used them as post-it notes for brainstorming sessions. We've used them in education, and we're really excited about other things that we can do with these more social swarms. So I think we're there. I think we have a chance to make these swarms a reality if we go ahead and do it to a certain extent. And actually, there's probably a little bit more to that. We'll have to make these systems more trustworthy. And so we've started just sketching out a checklist of maybe 10 things you need to think about if you want to make your swarm safe. It's really early days in trying to consider this. On the nanoswarm side, we're also working with bioethicists to understand what the regulatory framework might look like for the first in human clinical trials. And we're working on tools to make human operators in control of the environments that we deploy with swarms. So for example, in the cloakroom scenario, can we allow that operator to prioritize whether they care more about safety or performance or robustness or energy efficiency? Because you can imagine if it's an open environment that people can walk into, well, maybe you need safety to be first, and maybe the robots are a little bit slower. So these are trade-offs that we need to tension, and we need to understand how to present this to the user. And we're using map elites to basically come up with an illumination of solutions so that we can allow them to choose what behavior fits best, what the operator would appreciate to make them trust the system more. We're working on tools as well to detect errors in these swarm systems. And this is work that was presented at IROS this week, where we look at data basically from individual robots and try to track down what's a good marker for a failure. And then here you see these little pentagons around the robots that have failed. We can label them in real time. So if you think about this as layers, we start with KPIs, what everyone wants to optimize. I think the swarm performance indicators, the next layer, is what allows us to be out of the box. And then the trustworthy performance indicators or trust performance indicators is the last layer, and that's what allows us to ultimately make swarms for people. And what I hope it looks like in the future is that I open the door and I'm able to have a little swarm in front of my house, maybe a little bit like you have e-scooters in city that you can just use freely. And these swarms are part of the community within the city. They allow you to order croissant. They allow you to take whatever leftover food you have that you won't be able to use, send it to someone in need, allow you to exchange your clothes if you wanted to swap something with someone who lives a little bit further than just the door the door right next to you, and maybe some communal warehouses where we can all share this space and this infrastructure and resources so that we can make some of these swarm solutions a reality. So thank you very much to the Floriano Lab, the NAGPAL Lab, and the Batya Lab for some of the previous work. And then all of this is cross-disciplinary. So there's a lot of collaborators and wonderful work from PhD students and postdocs, as well as our funders. Thank you.
Thank you very much. If there are questions from the audience, please approach one of the microphones in the aisles. So I'd like to begin by asking about the nature of physicality, especially in the social swarms. From the video, it was hard for me to tell what are the ways in which the movement of the robot actually enables the types of interactions that you were looking for.
So we're exploring that, actually. So the paper we presented this week was a controlled trial where either people held the robot, so the fact that they could move around didn't matter, and then compared it to the moving scenario. So what mobility gives you is an anonymity. I can never say that word. But basically the fact that you can enter your opinion. People don't need to know that it's your opinion, but you still have power in that voice, and your voice can travel within that physical space. So if you think of a brainstorming scenario where this group is thinking of one thing, this group is thinking of one thing, they're not communicating, we hope that the physical presence of the robots allows these opinions to travel and allows people to brainstorm in a different kind of way. But it's very early stages in terms of understanding how useful it is, when it's useful. What we did see in that mall is that people came to answer this question about climate change who typically wouldn't engage, and they came because of the robot. So there's also just an element of engaging more people in these discussions than what you would typically do if you just had a screen and asked them to press a button. So it's early days. I think we're trying to understand where it has its best use, but we're hoping that these wheels actually allow some of these ideas to transport and engage more people.
Great, thank you very much. Let's take the question over there, and then next we'll go over here. So please start.
My question is that, Professor, you mentioned the learning approach, like pushing the plate to part of the arena, and the behavior tree approach. I want to ask, are this approach the centralized one or executed a decentralized way? And how to synthesize this like behavior tree? Are these synthesized automatically or by human? Thank you.
Right. So the way these systems are evolved is we define a certain number of behaviors we can include in our behavior tree. And then through evolution, we're able to select behavior trees that give us better and better performance. So there's really two ways to do that. One is you could do it offline. So you basically using a simulator, what you're going to do is you're going to, using a simulator, what you're going to do is you're going to, generation after generation of artificial evolution, improve your behavior trees, and then you're going to arrive at a good behavior tree that you transfer to the robots. So that's often how it's done. In the work that you saw with the Frisbee, that evolutionary process is happening on board each individual robot. So it's distributed in the sense that every robot is running its own simulation, coming up with its own swarm behavior, and they can communicate those swarm behaviors to their neighbors. So collectively, it's an island model. These swarm behaviors can propagate through the swarm. So it's a fully distributed mechanism that's done on board the robots.
Thank you. It's very amazing. Thank you.
Hi, thank you so much for the talk. I was wondering, as someone who's trying to make my own collective robotics, your thoughts on designing flexibility in the system itself of, do you make a platform of collective robotics that it can have multifunctional uses, or do you spend more time in the design process and kind of searching the design space and then building a specific swarm robot for the specific task that you designed up front?
I think it depends. So the latest robots, both the tiles and the dots, were built for specific applications, but have modularity embedded in them. So for example, the dots, the latest work that we did was to add an arm on top, because that plate can be removed and you can plug something else in there. And so you're able to adapt it as you go. I think things change so fast. I think it's worth thinking about how you can use this for a breadth of areas and then have the modularity, just enough modularity that you're able to expand on that. A lot of these things can be modular if you think about it. So the tiles, for example, they have 3D printing casings. You could design a completely different case around that. The dome, the one for the microsystems, 3 different projects have completely adapted it every time, and it's an iteration on what was already there. So I'd say it's getting started and doing it. It's a bit daunting because you're going to make 100, and what if it's the wrong design? But those first 100 are going to allow you to learn, and they're going to be useful for something in the initial stages before what your next iteration is going to be. So.
Great, thank you so much.
Hello, thank you for this great talk. I was wondering about, because I feel like it's really hard to put like a good application onto swarm robotics. And in nature, I feel like the reason swarm robotics or the swarm behavior exists is because each like small entity is not, you need like the power of a lot of entities to kind of overcome the problems or like the limitations that, for example, a small ant has. And in robotics, in a sense, we don't really have that problem because you can just build a bigger robot that does the task. So in a sense, the solution that swarm robotics is offering in nature is not really a problem in robotics. What's your take on this?
Thank you. My take is scale. So what swarm robotics offers us is scale. So where robots currently aren't deployed are huge areas that we need to cover. are areas where we need to explore the deep sea, but at a huge scale. Thinking about the logistics problem, I'm saying, is not just one warehouse, but what does a city look like if everyone has a robot? Driving, actually, it was given this morning as an example, also has this huge scale. So I think where swarms come in is when the scale is needed. And a lot of the real world applications we're not doing with robots now, because they require the scale of robots we can't deploy, I think have a footing in swarm robotics. So it's not so much about individual capabilities. It's about the size and the scale of what we're trying to do. And to be fair, I think you're right, we can make more capable robots. And so those last robots, we're trying to bring together both worlds, some of the more capable things that we can do with individual robots with the scale that we're hoping to achieve with many, many robots working together.
Okay, thank you.
Right, another question. Last question.
Oh, hello. So I think from the example that you gave in the biological sort of medicine type of avenues, where they're like 10 to the power of 13th scale, whereas in the today's robots, even the swarms with a decent size is about like tens and maybe thousands if it's big. So I was wondering, like, what do you consider to be the avenue to actually making swarms into a reality to achieve the level of scale that you're considering, that you've considered as like one of the benefits of swarm robotics? Like, what is missing, and what do you feel like is the core challenge that we still need to address in the field in order to make it actually a reality in the society?
So I think, for example, for the forest fire monitoring, 50 robots would allow you to cover the area of California really nicely. So the numbers aren't so huge for some of these scales. For the city scale logistics, I haven't done the calculation. It would be really fun to think about how many robots would be able to cater to a city. But because it's scalable, you don't need to start big. So with the cloakroom scenario that I gave you, you could start with 2 robots, 5 robots, 10 robots, and then think about how you deploy this with 100, with 1,000. And so where we're lucky with swarm robotics is that we can think about this starting smaller, I would say, and then building up to something that's the scale that would allow us to deliver on some of these real world ambitions. So, and I think a lot of the hardware that we can design now, we can scale up to reasonable numbers where we can combine both the swarm robotics aspect and the capabilities and the numbers to make that reasonable.
I see. Thank you.
All right, this will close the session. Let's please give Professor Hauert a round of applause.